Okay, it's my privilege today to introduce Prof. Volker Lenz from Germany, and he is from Research Institute, which is actually a company, but especially because most of its research is for the common good, gemeinnützige in German, so they have a special tax status on that. So translating is German Biomass Research Center, so they serve all of Germany there. And he will talk today on future perspectives of renewable heat supply from biomass in Germany, in particular smart biomass heat, as one possible pathway. And it is his second time to visit Japan. Now he's on a collaborative research visit together with researchers from Tsukuba University. And I met him at his first visit. There was a German-Japanese binational conference day on biomass energy, and he gave a presentation on that. So we look forward to the presentation today. So it's 1 hour, and just at the end, just 10 or 15 minutes for questions.
Yeah. Okay. Thank you, Dr. Hitzer, Professor Hitzer, dear attendants. I'm very appreciated to have the possibility to give this small speech and this small insight into, firstly, German's biomass heat strategy, development, and aspects, to give you an idea what's happening in Germany and what could perhaps be learnable also for Japanese technologies and Japanese development for the future. And then I will go to describe this smart biomass heat idea coming from the political background in Germany, what it's changing and why we do think that this is a possible pathway for the future and the use of biomass in a heating system. And last but not least, I will give you some examples of research and development on this topic and to come forward with this. So let me just introduce a bit the German Biomass Research Center. It's owned by the Federal Ministry for Agriculture. Here it's the only shareholder of our company, and we have a supervisory board of different ministries in Germany: Environmental Ministry, Research Ministry, Building and Traffic Ministry, and as well as the Saxonian Environmental Ministry. And all these ministers decide by their representatives about our work we do with our funding we become. Additionally, we have a research advisory council from experts from all over the world who give us once a year ideas what should we focus on with our research. Organized, we are in 4 departments, scientific departments, from whom 2 have a very strong link to the Helmholtz Center for Environmental Research. And this is one, the Bioenergy Systems Research, where we look to potentials, where we look to the integration of bioenergy into the state-of-the-art energy system and also into a future energy system where there are more renewables in. In the Biochemical Conversion department, they deal with all kinds of anaerobic digestion. They have a lot of reactors to improve these processes, to look into the microbacteria work and so on. Biorefinery department, they deal with all the liquid fuels and the questions of transport and so on, and developing by gasification and synthesis production of different kind of fuels. And Thermo-Chemical Conversion, that is my department, where we work with about 40 people on all the questions of innovative solid fuels. That starts with wood fuels, upgrading these by pelletization, by thermochemical conversion, but also all kinds of agricultural fuels, residues, byproducts, wastes, and so on. Then we have a working group for small plant technologies. There we look into boilers, furnaces, and so on, how to develop them, how to improve them, how to reduce the emissions and improve efficiency. And last but not least, we have a working group for the future where we develop demand-oriented small-scale CHP technologies that will be one part of the smart biomass heat idea. And they also concentrate on all the questions of controller systems and improving the work together of different energy sources and energy uses. So just some points of our main work here listed, and I've told you already. So what is the motivation for bioenergy in Germany? And this is clearly, I think, also true for Japanese conditions. We have in Europe some regulations about climate change protection. For the European Union, there should be a reduction of 20% until 2020, starting off the state of 1990. And Germany has accomplished that we will have a reduction of 40%. And in this year, our government noticed that we will probably not reach this target. So they have made up a plan to go for further measurements and further actions to come to this target. Worldwide, you probably know this target of not more than 2 degrees centigrade of more average temperature on the world. And some people discuss about if it should be 1.5 degrees or it's enough with 2 degrees, but independent from that, it is clear that we have to have a reduction of at least 80% of all the worldwide global warming potential emissions. And that means for industrial countries as Germany and probably also for Japan, we have to have a reduction of about 95%. And that's really a hard target. Second point is always energy security. There in Germany, we import a lot of energy as fossil fuels, but we have our own coal in difference to Japan, where I think about 90% of all the energy is imported as long as nuclear power stations are stopped. So the reduction of energy imports also for your economic development is a very important target, and to reduce these dependencies also from countries with unstable situations. And last but not least, connected to the creation of income and jobs is the target to use more your own values, your own biomass, bring it into your value chains, and by that create jobs and income also in rural areas and not only in the cities. And from my 2 visits, I learned a lot about that Japan has quite a lot of wood until now, but because of the history of the last decades, there was too less use, and now there has to be a lot of development to bring the value of all your forests into use and into new value chains. So that is very good linking to this target. So what is special about bioenergy? There are some chances, some challenges. First, the chances, it's most frequently used renewable energy in the world. About up to 80 to 90% of all the renewables worldwide is bioenergy. And that's, you can remember very easily if you think about the use for cooking and heating in the developing countries, but also in countries like Germany, I will show you later on. Any kind of energy solution is possible. So we can create from biomass heat, power, but also transport fuels. So in comparison to other renewables like wind or solar, where you typically get some electricity and sometimes also some heat, the biomass can supply all kinds of these energy solutions. It's storable, and so you can use it demand-oriented. There are local value chains, we discussed that already, and there is a global warming potential reduction potential in comparison to fossil fuels, and a lot more. But on the same side, there are also some challenges. We have a limited potential. That means that biomass have to grow on area. And area is, especially for Japanese conditions, a very rare source. And so you can also create only a certain amount of biomass. And as there are different kind of using possibilities for food, for feeding, also for material use, we will come possibly to conflicts. Sometimes from these conflicts, there could be a non-sustainable use of the resources. If you think about rainforests, there's always the problem if you take too much wood out of a forest, you can destroy it. And that is meant by non-sustainable. We have a limited standardization according, for example, to gasoline or diesel fuels, where there is very clear what is in such a fuel. We have in Europe some discussions, and there are also already started some norming activities. But as biomass can be very, very different, especially on the spur elements, and they have a lot of effect on combustion emissions and so on. So a lot of more work in the standardization is necessary to avoid high prices of the using technologies. We have a low energy density according to fossil fuels like gas or oil. So the demanding logistics can be always a problem. We have price impacts on coupled markets, I will show you soon. And also in some technologies, especially for the first stage of liquid fuels, the reduction potential of the biofuels is lower than 80%. So it doesn't fit to our target to reduce in industrial countries down to 95% of reduction. So you have to think a bit about possibilities there. Just to see in what's happening in Germany or what happens in Germany, in the green column, you see the material use of wood. There was an increase over the years, but at the same time, we developed, starting off 1995, the use of wood for energetic uses. And this was a really targeted development. In those times, prices for wood were very low, and the sawmills had the problem that they don't get rid of their residues. When they build up construction wood, they had about 30 to 50% residues from the stamp wood, and they can't use it. They were glad if they could give that away for free. And by increasing this energy pathway, we started to really increase the use of these potentials. And by this increase, and since 2007, we have more same, the market is divided in 50% each. There was also an increase in the prices. That seems bad at the first perspective, but at the second side, prices got up so that it was valuable to take more wood and more residues out of the forest. So only with this increase of price, you could manage to get the potentials be used. For the critical aspects of different utilization, I have one foil from 2008, but there's not much change about that. And it shows where the biomass, the worldwide produced biomass, goes to. And what you see here is about 50% is nutrition of people, direct food. And for energy purposes here, 10% from the forests, that are the residues. That is linked very well between a material use of wood and the energy use of wood. We've seen 50-50%. And we have a use of energy by renewable resources. That is really plant and farmed energy. And that is in contrast to this big amount of about 73% of 3/4 of all the planted biomass. And you see also that a very big amount of the biomass is just used for animal feed. And that means especially the usage and the eating of meat. So if we discuss about this small part, we always shouldn't forget about the amount of biomass we consume by our nutrition. For Germany, a short picture. This is all the final energy consumption in Germany 2013. About 12.3% come from renewables. And the biggest part, even if we talk a lot about wind power and photovoltaics, that has developed very well the last years, but still about more than 60% comes from bioenergy, and that in an industrialized country. And that is not used for open fires or things like that. That is really used for heating, power production, and so on. So you see that there is a big option to use biomass. Here also a graph about the different used biomass resources. You see biogas that has increased the last 5 years very much in Germany. So from the electricity production, there is always from the engines also a heat output, and that is this column very increased the last years. But at all, if you look to the solid fuels, that's waste wood, and also the other kind of solid fuels for direct heating, that is still about 2/3 of all the biomass energy in Germany. Another graph to show the development. What you see here is solar energy, it's heat pumps, geothermal energy. There is still a significant increase over the last years, but you see still solid biomass and also gaseous biofuels has a very big impact of all the heat production in Germany. So what are the usings for the solid biofuels? And what you can see here is that we have about 70% of all the fossil fuels from the primary sector is used in furnaces. And that means that we have about 14 to 16 million single room heaters. With a population of about 80 million people, we have 14 to 16 million single room heaters in private housing. And additionally, there are about 0.7 to 0.9 million woodlog and wood pellet boilers in your basement for a central house heating. That is very much more common than in Japan, I learned. We in Germany have some longer times for cold winter, and so people like to have a central heating system with radiation and air changes. And the heat output is about 15 to 300 kilowatt each. Then we have less than about 10,000 wood chip boilers with a nominal heat output of 100 to 3,000 kilowatt. This is especially for the heat supply of district heating systems. So to see what is the state of art for these technologies, we have the single room heaters here. We have the boiler technologies here for a pellet boiler or a woodlog boiler with a high efficiency and very comfortable for the users. Here's an example of a wood chip boiler with about 150 to 200 kilowatt thermal. And here is a typical heating system integration with a solar system, a buffer, and a small pellet stove with a heat exchanger to your central heating system. For these stoves, the market developed very well, also for pellet boilers. What you can see here, this is a column of the pellet production capacity. There was a jump in the years 2006 to 2007 when this technology integrated to Germany from Austria and Switzerland. And you see that then this development can rise up very, very quickly. We have installations of new units of about 20,000 units per year and reached already in 2013 about 300,000 installations in Germany. So what does the policy for these developments? On the electrical side, just a small insight, we have a Renewable Energy Act with a feed-in tariff. You have also in Japan integrated in the last years. We have a sustainability ordinance for biomass production to electricity and also a biomass ordinance where it's defined which kind of biomass can get a feed-in tariff. On the other side, for biomass heating, we have a market incentive program, especially also for private persons to get a financial subsidy if they install a biomass heating system. And we have a Renewable Energy Act for new buildings and also for bigger renewings of buildings. There you have to install a certain amount of renewable energies. What are constraints in Germany? In the biomass for electricity sector, we have a change of the Renewable Energy Act in 2014 this year, according to a long discussion about rising electricity prices according to the feed-in tariffs that have stopped or lowered a lot of these tariffs so that it is very hard to get new electrical power plants from solid fuels in the future because the feed-in tariffs got too low. We have very low CO2 trading fees in Europe at the moment. They are about 7 euros per ton. So there's not much incentive for big power plants for co-combustion at the moment. And we do not have any capacity fees for biomass, what could also be a kind of subsidy. In the heating sector, we have especially problem with a new or renewed small-scale furnace ordinance, where there are legislation on the emission level that is allowed for private boilers, and it is lowered by about a factor of 5, especially for particle emissions, and that is a real hard nut to crack for the developers to get along with that without precipitators. And the precipitation for these small units is just under development, and there are also some additional problems on that field. That, in mind, leads to a statistic about new installed heating systems in Germany. And what you can see here is that biomass is more or less the smallest amount and percentage of all the new installed heating systems. Most people try to do a better insulation so that they can get rid of this new need for renewable heating. And also a lot of people use air conditioning with a heat recovery. And for the real energy technologies, especially the heat pumps, are very favored. So to sum the status of bioenergy up, we have renewables in the sector 2013 about 24.5% for electricity, 11.6% for heat, and 5.2% for fuels. We still have the bioenergy as the most important renewable energy source, and there is still a potential from 1,200 to 1,500 petajoule per year, from which is used about 1,000 petajoule. So we can increase the use, but it is limited. The better prices for wood and agricultural products are good for the producers. They give them a higher income, and it's more valuable to create these energy resources, but at the same time, the biomass feed-in tariffs are among the highest ones, even after the reduction of the last time, because in solar energy, they went very, very down according to the better price development. We have not reached for many years the biodiversity targets. That's not only connected to the bioenergy development, it's a problem of our agricultural system, but that depends a bit. We have a need for more flexibility in power production. I will show you later on. And in the biofuels, I have already told there's not only enough CO2 reduction. So what restrictions are there for further bioenergy development in Germany? Biomass gets more and more scarce, I told you already. And in the future, we think that especially wind and solar will have to be the backbone of the quantitative production of renewable energy, because there are very, very big potentials. This is true for electricity, but also if you think additional with geothermal heating for the heat sector. According to the high fluctuation of these technologies, also for electricity as for heat, we need more storage and more flexible energy production. And if we keep up this 80 to 95% target for CO2 reduction in Germany, we have to change our energy sector totally to renewable energies. So the compensation of the fluctuating renewables cannot come from fossil fuels. It also has to come from renewables. And the demand for the heating sector has to be reduced by at least 80%. Otherwise, we will not have enough potentials to come to this totally renewable heating production, but that is possible by better insulation. So, is there a future for biomass combustion of solid fuels in the future? We think yes. But there is not the possibility for a massive quantitative increase in Germany anymore without imports of biomass. And that is, for a sustainability aspect, not political wished in Germany. And because of that, we have to have a change to more quality and less quantity in the use. And that is the point why we will come to other pathways of biomass use for heating. What we have to keep in mind for this research and development, we need sustainable biomass. So that means residues, waste, byproducts, because then all the need for the nutrition and so on of the planting is already for another purpose there. So the global warming potential reduction potential is higher. The system integration must be that kind that we at least reach 90% of reduction, also with the biomass technologies, and therefore a maximum of efficiency is needed. And always keep in mind, especially for combustion processes, we have the problem with the particle emissions. We should reach a minimum of environmental impacts from the exhaust gases as well as the waste. And clearly, we have to compare with other renewable energies, and only if there is in certain technology pathways an economic advantage, then we will have a chance in comparison to solar, wind, geothermal, or so on. That all means that for the future, we have to develop systems that have a high flexibility, that are regional adjusted, use the fuels and residues that are available in a region with a high additional value for the total energy system. And that means for us that we will change the quantitative use of biomass towards smart bioenergy. What is smart bioenergy from our point of perspective? It is a reallocation of the already big amount of biomass used worldwide, as well as in Germany, away from the traditional aspect of as many full load hours as possible, away from the baseload-oriented bioenergy to a more technically improved, more efficient, and more need-based use, and then a better integration in the total biomass system of material use and energy use. So, what we not can say at the moment is where will we go exactly, because that's in the far future. But we can give some criteria for new developments. The first is that we think about smaller biomass throughput. We did have the discussion in Germany about very big industrial installations with hundreds of thousands of tons of biomass be reformed to biofuels. That means that there could be 5 plants in the whole Germany and then bring the biomass for hundreds of kilometers to one plant. And if you think about that, a lot of people don't like that. That is easily to understand. And all these negative mass effects you can avoid with a higher regionality and smaller units. We have to be more efficient, clearly, and especially environmental sound, though that the neighborhood is not disturbed by this technology use of the fuels. And we need a better integration in the material and energy system. That means that we should couple a biomass value chain between the material production and energy production. If you look to forests, then try to get out as much as possible construction wood, and from the wood residues, you then can go to a good integrated energy production. So what means that for heat production? First, we should use firstly over solar thermal, geothermal, waste heat, and also if there is additional over electricity in the grid, then you can use that for heating. and then with small-scale biomass units, fill the gaps. Secondly, for more environmental sound technologies, we will probably go to pre-gasification in the combustion process or total gasification, then go to small combined heat and power production units with an intelligent buffer control system and also some catalytic gas cleaning system to go to very low emissions also during load changes. And last but not least, use residues, byproducts as fuel, and adjust your installation to the heat demand so that every energy you produce on the heating side is really used. And then look if you can produce additional power. And as heat is more easily be stored in a water buffer, for example, than electricity can be stored, you can produce your heat just over the time and over the day at those moments when the grid, your local grid, needs additional power to be stabilized. And that is an also aspect of integrating and better integrating into net and systems. So as a result for the heat production, in Germany, we like nice heat. And we want to be self-sufficient. And for these reasons, we are willing to pay some money for wood and also for biomass systems. We need a 100% renewable heat production for the future, as we've seen, to come to this 2 degrees centigrade target of climate protection. And that means a massive reduction of heat demand and the use of all kinds of renewable energies. That means for our development that the units of boilers must become much smaller. Nowadays in Germany for households we have boilers with 10 to 15 kilowatt, but in the future they will have not more than 2 or 3 or 4 kilowatt of power output. And so we need more flexibility in the heating systems, and in the long term we think of 2030, there will be these flexible micro-CHP heating systems. And that is the concept of smart biomass heat. And you see it here. This concept needs a conditioning of biomass and the regional biomasses to a high-end solid biofuel, so that can be good conformed and flexible converted by new technologies, which are more or less emission-free, and also CHP technologies. And very important are these innovative controllers for the system integration on a renewable heat and power grid system. And what I will show you now is some first technology examples and developments about upgraded fuels to enable this flexible operation. We will see some emission reduction options during flexible operation we are working on. Very flexible micro-CHP. Micro-CHP is about less than 1 kilowatt electrical. And a lot of people think and believe that that is not possible with solid biofuels, but I will show you an example of that. And also these advanced controllers and smart controller systems. So to start off, upgraded fuels is firstly the question of also torrefication. Torrefication is a heating of the material in either a batch reactor or a continuous flow reactor with about 200 to 300 degrees for 10 to 30 minutes. And by that, the material changes and gets torrefied more and more dark to a dark brown material. By this, you have a loss of about 30% of your weight, but only 10% of energy loss. And if you compact it afterwards with a pelletization, you can increase the volumetric energy input by about 30 to 40%. And that means that you come nearer to coal conditions and so have a higher energy impact. And so could look like these fuels. The FFPRI has just opened a new installation yesterday in cooperation with Sanyo Trading, and we are looking forward to cooperate there on the further development of these torrefaction systems. To show you some other technologies of improving fuels, there's also hydrothermal conversion aspects, especially for wet biomasses, hued sludge or things like that. There you go to a wet phase, put pressure and heat on, and by that there's a conversion also to a carbon-like material, and you can sieve it off the fluid and can use it like also a coal process. And what we are working also in Germany on is a washing and leaching of the material, where you can get rid of some minerals in the fuel. So what you can reach for these technologies improves the storability and grindability. It's especially interesting for co-combustion in coal firing or in dust firings or gasifications for biomass utilization. What you probably not can is to improve the emission behavior, because you don't change the ash content and the ash elements, because you can't get them off by torrefaction. You can create a high-value heating system and fuel from clean wood that it can be used in typical boilers, but there is a higher risk of slagging and clogging of nozzles, so you have to adapt the boilers. But what we've seen, and that is important for our smart biomass heat concept, is probably you will get a higher yearly or annual efficiency by using this torrefied material, because it is better and more flexible, adjustable to different part loads of your boiler. And at the moment, a lot of technologies for wood pellets are not very good on that point. In full load operation, they have an efficiency of about 85 to 90%, but if they have a lot of load changes, this efficiency goes down to 70%. So you have a lot of loss there, and that can be reduced probably by torrefaction. Washing and leaching can reduce potassium and chlorine, what is very important for the building of particle emissions, and the HTC can handle also wet residues, what is typically otherwise a problem for combustion systems, and also you are able to leach out some ingredients. For emission reduction, you see here one of our technical stands where we can have installed a boiler. There we can measure all the emissions, we can put in different fuels, and afterwards, after dilution tunnel, we have again the option to make research on the emissions that are created. And here is just an overview of the possibilities you can work on to reduce on primary measures the emissions. Fuel side we discussed already. Furnace construction is a question of the burning geometry. You can improve that also by computer fluid dimensional analysis. We have air supply questions, also fuel bed questions with cooling, moving of the grate, and so on. And also the control system inside a boiler. And additionally, there are also possibilities for secondary measures we also work on. There, especially in the small scale, there are electrostatic precipitators. Here, some examples of that. Gravimetric precipitators like cyclone are very familiar, already used. We have to measure these precipitators on a test rig like here, where there is a measurement opening in front and behind the precipitator, which is installed in between. And at the end, you see a boiler where we can create different kind of particles to be measured. Filtering systems and also catalytic systems are on the market. Now to come to the CHP technologies. From the past, we know in a very small scale, especially Stirling engines, that is typically for gaseous fuels. And they can work, but together with the wood combustion, it is a bit difficult, because typically on this hot side, you get a lot of particle forming on this cooling area. And from that, the system lose very quick their efficiency. What is very much on development is gasification systems with a motor engine on behind of that. So what you can see here is the gasifying and cleaning system, and then it comes the gas to a motor engine. Sanyo Trading is introducing another technology to Japan, that's Burkhardt, with a bit of a bigger size, and also using pellets for a better quality of your production. What we had for some years in Germany is biomass ORC technologies. It's an organic rankine cycle. So that means you have a biomass combustion, and then you go over a thermo oil circle, create an organic vapor, and that's a bit easier than a steam process, because the security aspects are not so high, but also efficiency is only down to 15% electrical. And then there are some big gasification plants and also waste wood power stations for steam engines with an electrical efficiency of about 30%. So what was the development in the last years? The steam plants with a big size were increased at the first time very much, but nowadays, because of scarcer resources and higher prices, lower feed-in tariffs, we got down to perhaps 2 or 3 installations per year. ORC technology had a short time of sharp increased development and then also stopped more or less at a stable amount installed. But what was very increasing the last years is this gas engine technology after gasification. And I say it can be proved in Germany and Austria that gasification systems from the right producer can work, also for a lot of full-time hours. And as I heard, Burkhardt has about in total 1.5 million hours of running systems. So that is quite a high number, and you can expect that if you have the right fuel change and do the right management and install the system correctly, it will run for the prospected 15 to 20 years. So what are the requirements if you go to a micro CHP? That's even smaller than these gasifiers with perhaps 30 or 150 kilowatt electrical. There you have some special requirements. What we defined is we would have a high electrical efficiency. 5% or 10% is just a game and not really useful. Additionally, we have to standardize the fuel. We see that with Burkhardt, they go away from wood chips to wood pellets, higher standard, clearer conditions. And if you get smaller, you have to have your process more under control, so standardize the fuel. Investment costs have to be low. You should have adjustable control, and you should optimize the overall efficiency at every operation condition, so at different heat production outputs. And from our point of view, to have a high value, you should be able to use all the heat. So first, adapt to your heat need and heat demand, and then your technology. So what you see here is a work of a student, a very first example, and only to show that it is possible to create such a thing, is a gasifier, just a ton, where there's filled in some charcoal from wood material. This is gasified in an updraft gasifier. Afterwards, the typical cleaning systems, a filter system, and then go to a mixing with the air according to the need of your power output. And then we went to a bicycle motor just to show that you can work with very cheap engines and motors. And then you can get over a heat exchanger the heat output. What you see here is the motor with the generator and all the control we added. And what you see here is just one curve. What we wanted to demonstrate is that we can adjust the load of the system on the electrical side very quickly and very strongly. So we gave the red line is what we wanted to have, and what the system reached by measurement is just the blue curve. And you see that it fits very well together, and that in a load range of about 100% to 20% in a very, very short time. Look here, it's about minutes. That means in about 10 seconds, we can have a reduction of power output of 80%. So we can control and stabilize the grid very well and very planned. Last but not least, controller systems. What we did in this project is to improve and develop a system controller and a real system controller. So there is a pellet boiler, he has its own combustion controller system. We have a buffer tank and a solar system, they have a solar system control. And we added an additional system that is linked to the internet for weather forecasting. So now we can adjust and can imagine when there is a solar input in the future. And that means that we can reduce the running time of the boiler. And what you see here, full load is on 100%. And the most time the boiler runs with about 20 to 30% of full load. That's the lowest load he can. And you see the total load over the time, 43%. And the system efficiency is about 75%. By integrating our controller, we can stop the boiler at the right time. It runs more time nearer the full load, so the total efficiency of the boiler itself rises to 57%, and also the system efficiency got up to 84%. To show additional figures, you see here if you go to an annual overall efficiency, is about 6% of gain, so coming from about 70% to 76%, and that's only by stopping the boiler operation. For the next step, we want to go into the boiler control so that we can give him also the load range that the boiler should work. And from that, we expect additional gains. Here in another graph, to see where comes these improvements. If you go to a changing day, spring and autumn, or typical Tokyo winter weather as now, you have some good solar production. You need room heating and hot water heating. And the pellet boiler just produces much more energy than is needed because he thinks in the morning your buffer is down, so the pellet boiler runs for a long time, heats the buffer up, and then you can't get your solar energy into the buffer, and it's lost just. So you can cut off 60% of overproduction by a good prognosis, and that we will do. And the last point is the question of controllers for system integration to improve net stability. And that is here to show for 2030 a prediction just. The different renewable energies, that red curve is the demand of energy in the system of electricity. And what you see here is that there are times when there's from photovoltaic more power generation from renewables in 2030 than the need is. And if you calculate these two, the production and the demand, you see that there are times when there's too less production of renewables, but there are also times when there's too much production. And you have to compensate that, either by stopping to produce solar energy, what's not really reasonable, or by, for example, the green bar is the bioenergy. You should, as it is storable, give the bioenergy systems a signal when they should run and when not. And for this development, that is the last slide, where we go then to the smart biomass heat concept. There we have a controlled system where we have the need-based flexible conversion technology, either combustion or gasification, to give a heat supply, or by a micro CHP technology, all the power for the time needed in the system. And here, for example, if you have your own house, in Japan, I've seen in Tokyo always these small solar systems and very small wind turbines. If you have such a system, then you can check also from a weather prognosis, when do you need additional other electricity production? That can come from this micro CHP. You produce heat, put that in a buffer, integrate also other renewables from the outside, waste heat, also overproduction of electricity, confirmed very easily to heat, and then you feed the heat demand in your house, in your object, in your region, and stabilize your local net. And that is the idea we want to go to develop with the small biomass heating system or smart biomass heat. So many thanks. Just the conclusions is to fill the gap, and we have I've shown, or I tried to show you, that there is already some technology step towards that, and now we have to go on in development to bring that to an acceptance also in the public and to fulfill the needs to make it marketable. So many thanks for your attention, and feel free for questions.
Thank you very much for this very interesting and very advanced presentation as well. Do you have a question?
First of all, thank you for your presentation.
Thank you.
And my first question was, on your slide, you said in order to make the 100% renewable heat production, you need kind of massive reduction in like heat demand and installations. And do you think you can talk a little bit more about like actual practical force that maybe the government may be conducting, or like how would we actually be conducted?
Yeah. In Germany, we have a special legal act that gives you some limitations if you want to build a new house. And there are also limitations if you renew more than one side of your house. Or if you want to change all your windows, you have to fulfill special standards. And these standards get more and more strictly every 2 or 3 years. And by that, there is a push. But the problem in Germany is that for the new buildings that works very well, and also on the European level, there is an incentive that I think by 2020 or 2025, in the future, new buildings all have to be passive houses. No others will be allowed to be built. But as Europe is an old country, and there are already a lot of buildings, new buildings are about less than 1% of all houses. So it lasts for at least 100 years to come to that. And also our rate of renewing the older buildings is down to 1% or less. So it will last too long to reach the targets. Therefore, in Germany, we are just thinking for the following year about some incentives of the state, that they give you perhaps a tax reduction if you invest in these insulation aspects and renewable energy aspects.
So that kind of like subsidies of the government is actually conducting right now? Or is it going to be conducted from now on, or is it already?
No, they think about that.
Oh, you're thinking about it.
That's a problem. They thought that it will run for itself, but as I told already, we recognized this year that we will not reach our CO2 emission targets for 2020, and now they are rethinking what can we do, and so they will probably think again about the tax aspect. They had a try 2 years ago, but then there were new elections and all the thinking stopped. And the problem with the state thinking about tax reduction and then not doing it is that people will wait to invest because they are still hoping that there will come this tax reduction. And no one will invest if you know, okay, wait a year and then it gets cheaper or you get a subsidy.
So for now, we don't have any incentive of making a passive house in Germany. Is that what you?
There are some incentives. You can get some better credit aspects, but you know all the states go down and down with the amount of money you have to pay to rent your money, and therefore it is not very interesting anymore, because if the total a building credit is already down to 3% or so, it's not much interest to do a lot of paperwork to get 2%.
My second question was about the controller for the system integration. And on the scale of 1 to 10, like how far the FDA research has gone right now in the current situation?
Okay, how far we are? Good question. What we are working on is in Leipzig, we had a project with the university that we tried to define and to connect different renewable energy production sources with a computer system, and then also looking how to control according to the demand. And what we installed in the DBFZ is already a very small solar panel and the small wind turbine I showed. We have our bioenergy technologies, and there we also are at the moment on a development to model that, to try to invent the necessary controllers and to implement them in the model and then prove that with real actions. So that is on a small base. And the main problem for us for the future is that in Germany, like in Japan, we have big energy producers, and all the regulations in the grid are made for big ones. And if you go with a 3 or 4 kilowatt electrical unit into the grid, it gets very difficult. And so when we have proven the technical opportunity, we have to think about the legal aspects and how to be able to integrate. Additionally, one has to say there are some big projects in Germany, not by the DBFZ, but by other research institutes in this context, where they tried also some bigger regions to control the energy from renewables and to integrate that also with electrical cars and so on, with not so bad results. But what our fear is a bit that a lot of these projects go to a very centralized control. And if you control everything very centralized, you get dependent on the one with the software and the controller and so on, and data security is a problem. So what we would like more is to look on the lowest voltage grid and then do a more or less automatic stabilization. You can measure the grid, and from power change and voltage change, you can see what is needed in the grid. And then perhaps get some information off the internet, but not give too much data back. And not give too much opportunity from a central controller to control your house. And that is also a question of acceptance for the people. Because I think it's hard to give the wife foreign control when she is allowed to wash her washings and her clothes. So that you have always keep in mind. Acceptance is a very important problem.
So it might take a couple more years to get it.
Yeah. I think for the smart biomass heat, also from the European policy, from industrial organizations and so on, we think that if we come to a marketable technology in 2030, everything is okay. So then we can have a market introduction that for 2050, all the new biomass systems should be like the smart biomass heat.
Okay, thank you.
Yeah? Thank you very much for your questions.
Yeah, maybe just a quick question. You spoke about capacity fee at the beginning for biomass. What is that?
What we think about in Germany is if you get more fluctuation from wind and solar energy, you need some capacity on a cold run that can jump in when wind and solar doesn't produce any energy. And at the moment, our market is only working on a price for work, for the amount of electricity you use, but there are some people who are thinking that in the future you should pay for a power capacity and not for the electricity you use. And for example, in Italy, there are some regions where your fee you have to pay over the year is calculated from the maximum power you've used once a year, and not by the amount of electricity you use. And for biomass, it is discussed, could that be a better way of subsidizing biomass, if it should be very flexible in running, or not, but that's open.
So basically it would be a reward for the flexibility
Yeah.
Biomass energy.
Yeah.
And then I have a question. What is the advantage of pre or total gasification?
Yeah.
Maybe you have explained it.
No, I didn't explain that. There are two advantages. First one is if you go to a direct combustion, you have higher temperatures in the fuel bed typically, and you get more exhaust gases. Because a lot of the minerals come out, it evaporizes and then condensates later on. And so you have more emissions typically. And also if you have load changes, your combustion is not so perfect, and then you get CO emissions and so on. If you go to a pre-gasification, and that in all combustion there is also a pre-gasification, but pre-gasification means that you separate your pyrolysis and gasification zone. That is your first reaction. And then you get more or less only CO and hydrogen and CO2 and water vapor as a product gas. And that you can easily combust very flexible afterwards in a separated combustion unit, or you can go to a motor engine. And your emissions are much lower, especially particle emissions afterwards. And it is much easier to be flexible because the primary zone you can run on a full load, and then you have a kind of small gas storage in between. And so it is, again, easier to react quick to changes in the load you need for be integrated in the system.
And what the two aspects would make it cleaner and more flexible?
Yeah.
But the kind of yield you have, the efficiency of the energy which is in the fuel and what you can convert, that is the same, or is there also a change?
That depends very much of your heat recovery, because where you lose the efficiency in the system is a bit by the needed heat for the gasification process. And as in a boiler, your gasification zone and your combustion zone are very near each other. So from radiation and the heat produced, it's enough to start the pyrolysis, gasification, and so on. If you separate that, you have to preheat your gasification zone somewhere. And that means that there is an additional need for energy and a possible loss. And by transporting, sometimes you have to cool the gas for afterwards using or for cleaning steps. And if you can't recover the heat from the cooling, then you have an additional loss. So the total conversion can lower a bit in the nominal load efficiency. But if you think of a very flexible running, then because of the higher flexibility, you gain it for the system efficiency back.
And anyway, if you use consequent combined heat and power, then when you have to cool the gas, this would be heat which you could also use as an output of the system.
Therefore, I mentioned and put the emphasis on the question, first use all the heat. Look what heat you need for filling the gaps and how you can store it best. And from that, the dimension of your technology or your smart biomass heat system is calculated. Yeah, it's heat driven. It's a heating system. And only in the second place, additional production of net stabilizing electricity. And it's not a question of amount of electricity, it's just to help to stabilize the net. Because the basic should be solar and wind, geothermal electricity, and so on.
But this pre-gasification or total gasification, the potential electric output would be higher.
Yeah, because first step is engines. Biogas engines reach already about 40% of electrical efficiency. If you think about a Stirling, it's about 10%, 15% for solid fuel systems. Gaseous systems perhaps up to 20%, but not more. OSC is also in the range of 15%. All these small systems still have very low electrical efficiency. And if you go to a motor engine, you can reach up to 30% in the small scale. And the last idea is to go to a fuel cell. And then you can go up to 50% and higher for the electrical efficiency.
The gas produced would also be the good material as an energy source for fuel cell instead of hydrogen.
Yeah, you can produce also CO and especially methane, and this methane can converted by the reformers to hydrogen for a fuel cell. And you have to think about the right gasification ingredient, not go with air, but with water vapor. And so you can increase the methane production in the gasification. And then that is the last step. If we reach to drive a fuel cell, then everything is fine.
Then you could get the maximum also electric output,
Yeah.
but at the same time, the fuel cell also produces some waste
Yeah.
heat, which
Yeah.
in combined heat and power could also be
Yeah.
used.
Yeah.
And then you could get even a 50-50
Yeah.
electricity and heat output. Do such systems already exist?
There are very small fuel cells in Japan. There is a fuel cell program for subsidies on a gas basis with natural gas that works, and also in a very small scale. And we have also a small fuel cell in our institute running with natural gas. For a first step, next would be integrating biogas, because there is a lot of methane, a weak gas. And then the next step is to come from the gasification process.
Oh, so very interesting developments ahead.
Yeah.
It's okay. It's our time already, sorry to go a little over time. Let's give a final applause.
Yeah.